So, hi everybody. I'm Ido. I'm with lakeFS, and with me is Amit. Hi, Amit.
Hey, Ido. Hello, everyone who joined on the call.
Yeah. So we're very excited today to speak with you about local data version control for MLflow experiments tracking. So that's the shortest title that we can come up with. We just shared some links about what we're going to use throughout this webinar. A few housekeeping rules, just so you guys know. Everybody's on mute. We have a bunch of people on LinkedIn. We have a bunch of people on Zoom. Throughout the presentations here, we'll be asking questions, and we will be and there is a Q&A button for those of you who are on Zoom that you can feel free to ask those questions, or you can ask questions on LinkedIn as well. And then we will monitor those. I'm looking at those also, and I will answer those as those come up. Everybody's muted, so if you have questions, please raise your hand, write a comment, write a Q&A question, and we'll answer those. Keep in mind that at least at Zoom, I believe you are anonymous. If you ask a question, you can choose to either ask it anonymously or not. Now, we're going to speak about machine learning data version control, and we're going to do this in the context of lakeFS, of course, and how to achieve experiment data sets reproducibility with lakeFS. Before we do that, just so we'll understand, it will be great to know if anybody here has heard of lakeFS before or not, just so we'll know how should we go, like really, because lakeFS does a lot of things. So if you guys can take a second and answer, have you heard of lakeFS before? Yes or no? That will be helpful, just so we'll know how that looks. I'm going to wait 10 seconds just to get your answers. See how it is. 5, 4, 3. Great. Amit, the majority is familiar or unfamiliar with lakeFS?
Not familiar.
Not familiar. Okay, great. So let's talk about, first of all, before we speak about lakeFS, let's talk about the day in the life of a data scientist, right? So this is what we typically see. We have a bunch of files that are not local. They might be on the cloud somewhere. They might be on the local, on a bucket. They might be of different formats. You can have image files, video files, annotation files that are stored somewhere. And I want to start working. I want to start, experimenting with the model. Then typically what I'll do is I'll sample that data, bring that over to my local computer with my GPUs, and then I'll train my model. I'll create it, and then the next thing that I want to do is I want to version it. Why do I want to version it? Because I want to be able to reproduce this model. I want to be able to collaborate between different data scientists. A lot of times we see that for compliance reasons, you have to make sure that you keep track of how you trained your model. You need to document it. And as everybody on this webinar probably knows, there is an element of experimentation. You want to change small things and run things again and again and again and see what the difference is. Now, a big elephant in the room is also, what do you version? What does version control mean in the context of machine learning? And there's also already tools out there that allow you versioning, right? For example, you can use MLflow, and this will have information of each experiment, right? That you run. But how do you version this? The data that you used, that you sampled, that you maybe also changed, right? To be able to audit and say, this is the raw data sets that then I changed this way and then I used to train this model. So then later after the fact, you can maybe run, after this finishes, another model. And that might be with the same sample data. It might be with a different sample data. And we want to keep track of that. And then we'll wait and we'll do it again. That's kind of the way that we work. And it's very difficult to keep track of all of these things. And today we're going to speak about lakeFS and how that will help you, how that will help version control the data sets used for machine learning experiments. If anybody has any questions, feel free to bring them up on the Q&A. But in the meantime, I'll go because it seems like nobody, or most people here are not familiar with lakeFS. lakeFS, just in a very high level, is something that you spin up in minutes in front of on top of an object store like Azure Blob, Google Storage, or AWS S3, or on-premises object store like Min.io, Dell ECS, NetApp has an object store, Hitachi has an object store, right? And basically, you take a bucket or a collection of buckets and you give them Git capabilities. So imagine that you can take a bucket and you can branch it, or you can make changes and commit those changes, right? Or you can roll back and address specific historical commits. And then the ecosystem of tools that we have in our environment will access the data through the lakeFS API and get those versioning capabilities. And from a refactoring perspective, if before we were accessing a collection on a bucket, now we will include a name of a branch or a commit identifier. A name of a branch would be prod test dev or experiment 1, experiment 2, kind of going to where we're going to go with this. And a commit identifier will be a point in time. So a commit can be, for example, for a specific experiment, the raw data, the modified data, the sample data, everything that was used to train a specific model and the model itself, as we're going to see over here. And then those Git actions themselves, we can run them through a notebook, through command line interface, or through a UI that we're going to see here also. Someone also just commented DVC. Yes, there are other data version control solutions out there besides lakeFS. By the way, what our solution today is going to show is the ability to work locally with data sets similar to DVC. Just because someone called it out, I will call out that the main differences are probably in scale and not probably for sure, in scale and in the ability to work with distributed compute. And if anybody has more questions about that, we'll be happy to answer. And if anybody wants proof, you can go and search the internet for, I don't know, other companies that have tried DVC. It did not scale for them and they moved to use lakeFS. Very happy to help point individuals to those as well. And the other solution is that the other difference is that what lakeFS does is, ironically, only version control for data, but we do that the best. So we believe that and that's what we do best. We don't play with pipelining and things like that. So we recommend using other solutions for those which are the best solutions in the market for things like that. Just to answer the comment in the chat. Any other questions?
Nothing so far.
Right. Okay, great. So I want to walk you through two things now. How does lakeFS works? How can you work with lakeFS locally? And then things that we're going to show you about the integration. So lakeFS works with lakeFS, you can choose to have your data completely stay in place, meaning you will have here a bucket like Azure Blob, Google Storage, Min.io as mentioned before. And you have a bunch of files here, and it doesn't matter what format those files are. These can be videos, images, annotations, Parquet files, iceberg tables, delta tables, doesn't matter. Every commit in lakeFS is a collection of pointers to objects that sit on top of the managed storage. And then we do copy and write. So when a new file is created, the next commit will point to this additional file. But files that did not change, like these 3 files, you will have multiple commits pointing to the same physical objects. The reason for this design is, there's a lot of reasons, but some of the advantages are that this is by far more performant at scale. right? Because if I, for example, create a branch, that's a metadata only operation, right? So we have thousands of users that we are aware of as an open source solution. Some of them have hundreds of petabytes of lakes, right? And branching will always take milliseconds because I'm not actually copying anything. That means that every experiment can have its own separate branch, and that would be without copying a single file. And also going back in time, it's a very effective thing to do because by nature on data lakes, a lot of times, most of the files are static and then a smaller subset of the files are added and removed on a regular basis. So de facto, we are deduplicating the object store over time. Now, this is how you work with the data where it stays in place. In the case that you want to actually bring data locally, which again is not a requirement, but calling this out, you will have a commit that points to a bunch of files. And then what I can do is I can run a lakectl local command that will clone these files from this branch to my local computer. And then if I choose, for example, to change this file and write a new file, when I commit those changes, then new commit will point to this additional file similar to what we did before. Again, this is a highly performant solution. And even if you have hundreds of thousands of files, lakeFS will very effectively find the difference between those files. And in the demo that we're going to show you today, we're going to show you three versioning in a way. One will be, first of all, we'll have our cloud storage with the data sitting in the cloud. And we will want to run, as a first step, some sort of training of a model on my local computer, right? So with lakeFS, we're going to have the data repository, right? That will have the different data files at scale, as mentioned before. A commit in lakeFS, right, may also include the MLflow experimentation details pointing to MLflow, and I'll talk about that in a second, and the git commit ID pointing to the code, which I'll talk about now. We will use git for the code repository. This will have my code files. This will also include a lakeFS commit ID. We'll tag a lakeFS commit that we tag, which means that I can see what is the data set that I used with my code. We'll also use a git ignore file that will make sure that when I work with the data sets in lakeFS, I don't try and version those at git, which does not scale, right? And on MLflow, we will manage the versioning, the different versions of our experiments. We will have here different runs. And again, these runs, when they have their models, will also have the lakeFS commit ID pointing to the data set that we use to train the model for a specific run in an experiment. So everything is kind of going to work together with a single notebook that we prepared for you, which is the same one that we did before. Let's see. Anything to add, Amit?
No, I think it's fun to see that demo. When we go through that, things will get very clear what you were talking about, like how we version the code data as well as the experiment in different tools and how we link all those things together. But before I start, let me ask one more question here, like what's your technology stack is. So accordingly, I can tailor my presentation. So please go ahead and answer these questions. Pause for 10 seconds. Okay, so let me share my screen. I'm going to end this poll. And I see a lot of people are using cloud. Most of the people, yes, different orchestration tools. And also they're using different experiment management tool like MLflow, Tensor, etc. Okay, so let me share my screen. 1 second. Ido, can you confirm you can see my screen?
See it clearly.
Oh, okay. So as Ido mentioned, today we are going to use a notebook, Jupyter Notebook for the demo. So this is the link to get to our sample repository, which includes the notebook and all this, everything you need to run this demo. So let me just go to this link here and just walk through quickly. So this is our lakeFS samples repository. Within that, we have this image segmentation demo, which I'm going to present today. And here you have instructions, like what are the prerequisites? You need a Docker. I'm going to run all those things locally on my laptop in a Docker container environment, and also requires the lakeFS server. And I'll explain how to use that to create the lakeFS server. One is you can sign up in the lakeFS cloud to create the lakeFS server, or you can install locally. And in this case, I'm running the lakeFS locally. So you can go to our website and our documentation, and there's a quick start to run it locally also. And also in the samples, if you do the main sample will also install the lakeFS container locally also. Next thing you do is git clone the repository and then build this container and run the container. So right now I'm running these two containers. One is my image segmentation demo container, which is using these instructions here. And then I'm also running lakeFS server locally. You can run in the cloud, or you can run locally, or you can run in any environment you want. So in this case, I'm running my lakeFS server locally in a container, but this one points to my storage endpoint is S3 or AWS. The lakeFS server is local, but the storage where I'm going to store my repository stuff is in the cloud and AWS S3. So that's my setup for the demo. Next thing is, let's walk through quickly about this demo, what I'm going to present today. So for this, I used this free data set available on Kaggle. It's called Airbus Ship Detection Challenge. So what this provides, it provides about 200,000 some images, the satellite images, where it has the boats or ships, and you have to train the model to find if you get the new image, a satellite image, to find if there are any ships or boats in that particular image. So that's the data set I'm going to use. It's a big data set. It's a lot of time people have millions of images. In this case, it's only 200,000 images. So if you want to run this demo on your own, you basically download these images and then upload in your S3 environment. So in this case, what I did, download all the images from this Kaggle dataset and then upload it into my S3 bucket here. So I had this one dataset has the training images, train and test both. And also it has another CSV file, which include the masking for those images. What masking is, the mask will tell you for the training images where the boats or ships are in that particular image. So that's the masking information, which is in the CSV format. And then you have all the images also in the training data set, as well as the test data set. So that's the data set I'm going to use for the demo today. So let's go back here. So anything else either I forgot to mention regarding the demo before I actually start the demo?
No, I think we're good. This is everybody can, I think the main idea is that anybody that wants to try this out can try this out on their own really, really quickly.
Okay. So once you get this container up and running, this sample container, there are different ports open here. So one is for Jupyter Notebook. If you just click on that link here, it will take you to the Jupyter, this notebook. In this case, there's this image segmentation setup notebook, which is for setup required. And then this is the main notebook here, which talks about running this demo in local as well as in the distributed environment at scale. So a lot of time people test initial or build their model locally, but when they want to run it multiple times, train it multiple times, they want to run that in the distributed environment. And that's where you can run this this notebook in distributed environment also. And in this case, we are using Databricks to run that at scale. And I'll talk more about that. But today, we are going to focus more on the how you train this locally and the version control everything. And then if you want, you can run the same notebook in the distributed fashion to run those experiments hundreds of times, thousands of times with different parameters, to see which model performs the best. So that's the notebook it does. So I'll walk through the notebooks, but today I'm going to focus more on how you run this thing locally. So this one, as I mentioned, this is my kind of target architecture here. So what I'm going to have is Delta Lake or Delta tables. So we'll take all those images, that image data set, and then convert into a binary content and store in the Delta tables. You don't have to do this, but for this demo, I'm just storing that as a Delta table. And then I'm using the PyTorch, Lightning PyTorch for model training. And to feed the data from Delta tables to PyTorch, I'm using Petastorm. This is open source library to feed the data in a format that PyTorch can understand. And also it can support the GPUs also. So if you are using GPU for your training at scale with large data set, then this sample demo will work with the GPUs also. And this Petastorm library to load the data will work with GPU also. And using MLflow for recording all your experiments. So in this case, even I'm running MLflow locally also for experiment tracking. But if you are running in the distributed environment, let's say in Databricks also use MLflow. So it will record all those experiments with all the training details and the version of the data which was used, what model was used, all those things will be recorded in MLflow. So that's kind of target architecture. Let me just quickly walk through what I'm going to do here in this notebook. So first we'll create the repository in lakeFS. And as I mentioned earlier, lakeFS server is running locally, but it points to the object store in S3. So we'll create the repository, and then we'll create the local experimentation branch. So in that branch, basically you will import some of the images from that image data set, which is about 200,000 images. But when you're running locally, you may not bring all the 200,000 images. So you might include only a couple of images, let's say 1,000 images or 5,000 images, whatever your local computer can handle. So that's what you will include in that local experiment branch. And then when you clone that experiment branch to locally to your laptop, it will automatically download those images to your local laptop. So let me repeat again. So we have stored all those 200,000 images in S3. We'll bring that, import that into lakeFS repository in a local branch. So instead of importing all 200,000, we'll just bring only the images that you might need, let's say 1,000 or 5,000, and then clone it locally to your laptop or your computer, and then you run your model training. Before you do the training, you might run through a data pipeline. You might massage your data set. You might delete some of the images. You might add some images. In this case, I have a pipeline. I'm not going to go too much detail on the pipeline, but we have a raw data set where we start with these images. Then we convert into a branch data set, which is basically converting into a binary content and saving a delta table. Then I'm going to resize my images, transform the mask information, the masking information, which is in the CSV format, which looks like this, convert that mask into an image, black and white image. And then that becomes my silver data set. Then I'm going to join my original image to the masking information so we can see where the boats are in the particular image. That becomes my gold data set. That gold data set will feed into my PyTorch Lightning model for training purpose. And to feed that, we are going to use Petastorm library. So that's what I'm going to do, and then record everything, all the experiment training in MLflow. And once you are done, let's say you run this model multiple times, multiple experiments, then you pick the best model from that MLflow, like based on those metrics you are tracking for best model. And then you can merge that information or save that information into lakeFS repository for future reproducibility purpose. So that's very high level. Anything else you want to add, Ido?
No, just to say, every blue circle here is a commit, right? So that means that you get this lineage. And at the very end, when you want to go to a specific model, you can go and you can see what was the gold data set, what was the silver data set, what was the bronze data set, how did it start with? And you have this full audit and full ability to reproduce the model if you wanted, if you needed to do it in the future.
Oh, that's a good addition. Thank you. Okay, so now let's start this notebook. So here in this notebook, you'll do initial some configuration step. Here, there are a few variables you define your, like for example, lakeFS endpoint. So as I mentioned earlier, that I'm running this lakeFS server locally in a separate container. So if you are familiar with Docker, if you want to access the other container, you use this host.docker internal to connect to other container. In this case, the lakeFS server is running on 8000 port. And this is my lakeFS access key and secret key. So let me open the lakeFS server from here. So if I go and click on this link, it will open my lakeFS repository here. So this is how lakeFS looks like UI. Currently, I don't have any repository. With this demo, I'm going to create the repository. I'll walk through everything. But let me show you how to create this access key. So here you go into administration section and just create your access key, record access and secret key both. So secret key will not be stored here, so you have to copy and paste it somewhere, but I already created my access key, so I don't need this. So once you have that access key, so you specify here the access keys, and I'm storing that in a variable. Next thing is repository name. So what kind of repository you want to create. So this is just the name for creating the repository in lakeFS, and where this repository will reside. So you have, there are two buckets I'm going to use here. One is where all the images are stored, which is my this repository, sorry, this bucket. And then I'm going to store my lakeFS also repository in S3. If you want, you can store the lakeFS repository locally also. But in this case, I'm going to store my repository in S3 in case if I lose something on my local laptop, I have everything as a backup on my S3. So that's my storage namespace. So here you specify the bucket name plus any prefix or folder within that bucket. So that's where my storage. Next thing for this local experiment, like how many images do you want to include in each experiment? As I mentioned earlier, I have 200,000 images, but to run this demo very quickly, I'm just going to use 100 images. But based on your resources on your computer, you can increase that size to 1,000 or 5,000, whatever you need. Next is where is this image demo data set is stored. As I mentioned earlier, it's stored in this particular container on my AWS S3 region, AWS region. And this is where my data set is stored, images. So that's the variables to store that information. And then also my access key to connect to S3. So this is my personal access keys to connect to my S3 bucket where the images are stored. So that's the configuration section where you define all those variables and set those variables. Next thing is the setup. So there's a setup notebook. I will not go through the whole notebook. There are functions defined in that, and then it will also create the repository, lakeFS repository. So if I just create this repository right now. So if I go back to my lakeFS UI, so now I have this repository. This is the name of the repository which you define the variable, and this is where the repository is stored on S3 bucket in this particular path here. So if I go here right now, this repository is empty. There's nothing else. So just quickly walk through the UI for lakeFS. So here, within the branches, you can see what your objects or data is stored. Any uncommitted changes or any commits, you can, as well as you can create multiple branches. Right now, I have just main branch and an empty branch. Then you can define your tag. When you commit anything, it assigns a long commit ID, but if you want, you can tag it also, which is more meaningful, which you can use. And in this demo also, we are going to create some tags, so you'll see that. And you can also compare different branches, the changes between different branches. Let's say you're running lots of different experiments locally also, and using different images, data set, then you can see the difference between like what changes happen between those two different branches. Then we have something called Git actions, where you can do like a lot of checks when you run any commit or when you create any branch. A lot of data quality checks. You can do a lot of automation through actions, and also this is just setting here. Won't go into too much details on setting. So that's a very quick overview of how the lakeFS lakeFS repository or UI looks. So next thing. So now my repository is ready. I'm also going to create the Git repository, so which I'm going to create locally. So right now I don't have my Git repository here so far. So I'm going to just initialize my repository and just do some initial configuration. You don't have to change this email, and you can just use dummy email for configuration and dummy name. So now I have this Git repository, the same repository name I used for the Git also, image segmentation repo. Right now, my Git repository is also empty. There's nothing in there, as well as my lakeFS repository. Okay, so this was all initial setup. Now let's start the real demo. Before I start, anything else either I missed or anything else you want to add?
I think we're good.
Okay, excellent. Okay, so next I'm going to create the experiment branch. So let's say you might run this local experiment multiple times. So I'm just defining this variable to run the experiment branch. This is my first time I'm doing it. So experiment branch 1, and create this branch in lakeFS. So this will create this particular branch in lakeFS repository. So if I go here into my branches, I have my local experiment branch here. You can also create the branch from the UI if you want to, or you can, in this case, I'm using the Python client to create this branch in lakeFS. And I'm creating this branch so where I can import my data set. So next thing what I'm going to do is get the list of all my images from S3. So as I mentioned earlier, around 200,000 images. So what it's going to do is going to go to my S3 bucket and get the list of all the images, not download the images, just to get the metadata about those images, the list of those images. And then I'm going to randomly select, in this case, for example, 100 images per experiment. A lot of time people use a labeling tool or something to pick those images from, let's say you have millions of images, you want to train your model based on certain criteria. So you might define your filters to based on some metadata. You might filter some of the images, or you might use some labeling tool to get the list of the images that you want to use for your model. So in this case, as I mentioned, I have about 200,000 images, but I'm going to randomly pick some 100 images in this case. But it's up to you what number of images you want to bring into lakeFS repository for model training. The next thing is I'm going to import those 100 images into the lakeFS repository in that local experiment branch. So if I go to this particular branch, right now this branch is empty, there's nothing in there. So I'm going to import those images. And when I import, I'm not copying the data from my S3, where the images are stored in S3, to my lakeFS repository. I'm just storing those pointers to those files. So that's why import goes very fast. So I just imported 100 images, plus the masking information, also the masking CSV file. So that took about like 2 seconds to import all those images. but you can import thousands, 100,000, whatever images you want to import, bring into lakeFS repository. Again, it's just the pointer I will show you here. So now I have my raw data set here imported. So in this case, I just imported those 100 images and the masking information, which is a CSV file. So if I go into this particular images and just quickly look into one of the images, I don't see anything in this image. There's no ships or boats. And then you can also look into the information here. Where are these information or these images stored? So in this case, if you look into the object information here, you'll see the physical address is this. So we are not storing this image in lakeFS repository. It's just the pointers to those files which are stored in this S3 bucket. But the repository is stored in another repository metadata. lakeFS repository metadata is stored in another S3 bucket. But the image data set is stored in a separate S3 bucket.
Yeah, this is the common thing that we see when people get started. And especially in these cases, obviously here we're showing just taking a sample of files, but we often see people importing data sets from different directories, different locations, and bringing them over. And what we start seeing here, the first thing that we saw is we created in our repository, in our experiment branch, a raw directory. And this is basically all the raw data set. And imagine that you imported this for many data sets in different areas, in different buckets. So these are all the files that you're starting with.
And also sometimes you might have some data set locally also. I'll show how to bring your local data set also.
Right. That's a good point.
So next, couple of variables to define my repository path in lakeFS. So next, when I'm going to create this locally, I'm going to bring this data in my local folder, which will be this folder name. You can have any folder name locally to bring the data from lakeFS repository locally. And then you'll add your own data set or you delete some data set locally. So this is all variable to define different path. Next thing is, as Ido had mentioned earlier, there's a command called lakectl local. This is lakectl is a lakeFS command line interface, CLI tool, and it has a local option where it will clone this particular branch, that experiment branch locally into this my repo path locally. So in this case, this is my local path. So I just cloned that repository. In this case, it downloaded all those 100 images plus a masking CSV file locally. So if I go into my local folder here, or I can also see from my browser also here, the file browser. If I go here, I can see all those files here too. So you can access those locally through your file browser also. So here I have my raw data set. Again, the same thing you saw, all the images that you saw in lakeFS repository, same are downloaded here in this case. Luckily, I found a boat here. So now we have all this data set cloned locally. Next thing you will do is let me explain how we integrate with Git. So Git will be used to handle the code versioning, while lakeFS will be used for versioning your data set. So if you look into this Git ignore file, so here you'll see that it's ignoring this particular folder, this lakeFS folder here. So let me go back here. So this folder will automatically get ignored. So when you clone the repository into this particular path, we automatically updated this git ignore file, and it tells that ignore this particular folder where your data set is stored, because we don't want your data set to go into the Git repository, because sometimes your data set can be terabytes of data, which you don't want to upload into Git because Git cannot handle the largest big data set. So that's where you are ignoring that data set to go into a Git repository. But we also create a lakeFS, automatically create this lakeFS reference, a YAML file, which includes the commit information about lakeFS. So when you commit your code, it will also commit this YAML file which includes the commit information from lakeFS about the lakeFS. So let me show you that particular file also. So in that case, in this YAML file, which is here, stored here .yaml file. If I go into my file browser, I can see this file here. And that file includes the source information, which is lakeFS source. In this case, this is my repository. This is my branch information. And this is my head or commit information. But so that file will not be ignored. So if you see here, it's not. So don't ignore this YAML file. So this YAML file will get checked into or committed to your Git repository. So Git repository will have your code and this particular YAML file, which includes the lakeFS commit information. So that's very important. So that's how we integrate. And also when you commit any changes to lakeFS, we'll automatically get the Git commit ID. So this is all happening automatically. You don't have to worry about anything. Once you git clone, it will take care of all this YAML information and the Git ignore everything automatically. Okay, so next thing is, let's say you have some, you have now local data set, but you want to delete some files, you want to add some additional images. So that's what I'm going to do locally. In this case, I'm going to delete a smaller image based on the size, but you might have different criteria. If you are using some labeling tool, you might say, out of these 1,000 files locally, delete those 100 files, 100 images. In this case, I'm just using a size to decide that, to delete those files. And then I'm also going to add some additional images. So in my case, I have locally this additional data set. In this case, I'm just using 3 additional images. Again, I can see from the browser here. If you want to bring additional images, just copy paste here. So those are 3 images I'm going to add. So in this case, so when I delete smaller files, so you can see here, this is, I'm running the diff branch. So you can see the difference between your experiment branch in the lakeFS repository and what changes you made locally. So in this case, I removed these 2 files because these 2 files are very small, and I added these three files, and there's just some checkpoint. This is Python, Jupyter Notebook checkpoint, so ignore that. So that's changes that happened in my local. And now also, let me add changes to Git repo and perform my initial commit. So what I'm going to do is, so far, we change the git ignore file, we create the lakeFS reference YAML file. So I'm going to just commit those things in the Git repository and make my initial commit. So I'll get the Git commit ID, which I'm going to use it to commit into lakeFS, and I'll show you that. So in this case, I'm just added all the changes into Git repository and made my initial commit. So in this case, initially just these 2 files were added into my Git repository. Next thing is I'm going to commit my changes to lakeFS repository. And so first thing, I just committed my changes into Git. In this case, as you can see, it did not include any images or the data set, the raw data set, only the YAML file, which includes the commit ID, commit information about lakeFS. Next, I'm going to commit my changes to lakeFS repository, which will commit all the changes that I made locally in my raw data set. In this case, I deleted 2 files and also added a couple of images, so you can see the changes that happen. And it committed my changes into my lakeFS repository. So if I go into my commits for this particular branch, so you can see this is my commit message, which is here, deleted this. And then when you commit, you can include a lot of metadata also. So if I go into this particular commit, so you have, in this case, automatically it includes the Git commit ID. So this is the one when I initially did the Git commit, that was my commit ID initial. So that's also automatically gets stored in lakeFS repository. So everything is all happening automatically. In Git, it stores the lakeFS commit ID. And in the lakeFS, we store the Git commit ID. It's all automatic. You don't have to do this all anything manually.
So what happened here is that we got some raw data, and then I decided for some reason that some files I want to edit. So I added some files, changed those files, and we still keeping that lineage, right, of everything that happened for me to get data for my model. So I guess now I can start working on my model.
Yes. And also something to add here, I forgot to mention that here with a single commit, you can see what are the changes that happened. So like if I say calculate the changes, it will tell you how many objects were added, how many objects were removed. And so if I go here, you can see these two files were deleted and these 3 images were added. So it's the same thing which you saw earlier here. So these 2 images got deleted and these 3 images were added. So that's also maintained in the lakeFS repository. So as Ido mentioned, you have full lineage, what changes happened, what things you deleted locally, everything is recorded in lakeFS repository for reproducibility purpose. Okay, so let's continue here. So now we got everything set up. We have lakeFS repository, we have a Git repository, everything is getting tracked. My data set is locally. Now let's run the pipeline and then train my model. So next thing is I want to just read my local data set. So in this case, I'm going to use Spark to read my data frame. Spark and a lot of other tools work with lakeFS. So I just specify my training path here or the data path here, and it will go to that particular path and read those files. So in this case, just showing the top 20 rows. So these are the images which are stored locally. In this case, my repository or this experiment branch is locally. But if you run in the distributed fashion at let's say in the cluster somewhere in a server, that will point to the lakeFS repository. In this case, mine is all local here, but automatically it will point to the lakeFS repository when you run in the distributed case. In this case, I'm just making sure I can read the data set and get some metadata about those images. Next thing, let me run the pipeline and quickly walk through here. So I'm just running in the background. What I'm doing is ingest the raw images and convert into bronze data set, like converting into binary content and save as a delta table. And all those things are happening locally. So if I go into my, one second, if I go into my local repository here, so now I have my raw and the bronze data set. So if you look into bronze, so these are the files, images which got converted into binary content and saved as the delta tables. So everything is happening locally. And again, you can run the same thing, same kind of notebook in the distributed fashion also, where it will run on a cluster. So now this pipeline is creating my bronze data set, silver data set. So let's just quickly, and after each data set, each changes I'm making, I'm committing my changes into lakeFS repository. So anything which is happening locally gets saved, committed into lakeFS repository. So in this case, after I create this bronze data set, I added those delta tables. So it uploaded those delta tables also in the lakeFS repository. And then I create the silver data set and gold data set and so on. I won't go through the full pipeline. So everything, as you can see here, all these data sets are available here. And then after each one, I'm just committing all my changes. And if I go into my lakeFS repository, I can see everything. Let me select this particular branch. And so after each processing raw data set, bronze data set, I'm committing all the changes into, let's say, for example, in the silver data set. So here also have, again, git commit ID, plus all the changes that happen in that particular commit. Like in this case, I create this silver data set, and it has this delta table. So all that lineage is available here in lakeFS repository. So you can see everything, what's changing in each step as you make all your commits. Anything else? Sorry, you want to add? I think there's one thing here. You can see the parent, like if you make any change, you can see what the parent was. So you have full lineage, as well as there was a blame functionality, which will tell you the whole detail, like what changes happen. Anything else either you want to add, like about the commit, how we handle it?
No, there's full of good things to add here. I'm just looking at the time, so
Okay.
I'll save them for another time.
Okay. So I need to run quickly then. Yeah, we have only 10 minutes left. Sorry. So next, I'm going to train my model. In this case, I'm going to take my data set, which is gold data set, which is ready with, I have a masking information and the satellite images, so are combined together. So just verify my data set looks good. And now I'm going to take that and use Petastorm. I'm going to take that data set and split into 80-20, like for training and test, and then use Petastorm, which will create this cache and then load into my model. So this is the next thing, is running this model. In this case, I'm using a particular parameters. In this case, these 3 parameters I'm using to train the model. But a lot of time you might run with multiple parameters, multiple times, multiple experiments you might run. So it's just finished. So you get this metrics output. So if I look into my MLflow UI here, quickly refresh this. So this is my run just happened, just this model run. I'll come back to this and go into more detail. What are we doing, storing here? Then let's say you run this model 100 times on your local laptop, then you pick your best model. So based on this metric, that IOU metric, intersection over union metric, you pick the best model from all the models information stored in MLflow, and then you save the best model information in lakeFS repository. I'll show that. So again, all this information we store in a best model file and then upload into lakeFS repository and commit my changes into lakeFS repository. And then I can also flag my best model for production ready in MLflow. So if you are familiar with MLflow, you can just mark as a production ready. And then let's say once everything is done, I have this notebook or code ready. I can copy my notebook or code into my Git repository. So if I go here and look into my Git repo, my code is also here. And then I add those files into the Git repo. And next, so now let me explain everything, how we are recording all that information in different places, like all the commit. So if you go to my lakeFS commit here, so this is information on the best model, which we stored in lakeFS. So here we have all the information about the MLflow stored in the metadata. As I mentioned earlier, you can store as much information in your metadata. So in this case, we are storing the model name, the model run, as well as all the details about the model. From here, you can also go into your MLflow straight away. And this is the run which was used for this particular model training. And here we have all the artifacts, including your pickle file, which is the model. Plus, we also include the data set, which was used to train this model. So this is basically a data set, which was used to train this model. So if I just take this URL, and it will take me straight to the data set in lakeFS repository. And you can see here, I'm using a tag here in this case. So this is my gold images for that experiment branch for a particular tag. So as I mentioned earlier, we create, after each commit, you can tag it. So you have meaningful names. And this is my tag I used to, this commit that I used to train this model. So that information is also stored in MLflow. And also here, the data set, you can see this is my gold data set with all the schema for that data set, which is also stored in MLflow. You also have these parameters, which I use for training all the metrics, the output from that. And there's a lot of tags we are including in this case in MLflow. For example, what's my repository name, lakeFS repository name, the branch name, as well as the data set, which is the same as this I showed earlier. So all that information is getting tracked in MLflow. And in lakeFS, we are tracking all the information about the model itself. So in that case, the Git has, so going back to this slide here. So we store in lakeFS, we are storing the data set, versioning all the data set, which also include the MLflow information in lakeFS repository, include my Git commit ID also in lakeFS. And in Git, we have this, the lakeFS commit ID, which is in the YAML file. And in MLflow, we have all the information about the data set, which includes the lakeFS commit ID or the tag, which is basically a tag commit. So all that, everything ties together. And all those data sets are versioned. The code is versioned. Your model is also versioned together. Anything else you want to add, Ido?
Yeah, that was incredible. Thank you. There's a lot of moving parts here. If you can give me the opportunity to share, that would be great. So just picking up from where you dropped off. So yeah, I think this helps understand where everything sits. There's a lot of moving parts here. And before we go, I just want to make it a little bit more complicated or actually a lot less complicated. We did a lot of things just because we're used to copying data locally. This notebook, as it is, you can pick it up and run it in Databricks or on some sort of other notebook that you wanted, and kind of take advantage of the fact that you have your data maybe sitting in the cloud, but you can also use the cloud distributed compute. So you can use your notebook, and that can be as in any notebook that you want to have, and you can basically use with lakeFS. You can train the model using things like Spark ML. You can train the model using distributed compute without the data ever coming locally, and I think that's very powerful. And we're not going to, because of timing constraints, we're not going to go into that in details here on this call, but it's important because it means that you're not limited to whatever your size of your computer is, your GPUs, right? Instead of using 100 images, you can use 10,000 images if you think that's helpful. B, you can run this in parallel, right? You can theoretically run as many compute as you need and just have, instead of waiting and doing one experiment after the other, you can do this at scale. And that's kind of the future of what we see people using lakeFS together with in their ML pipelines. Again, I'm not going to speak about that here, but in a very high level perspective, what we saw today is ability to run things faster, reduce risk, save on storage, and achieve full reproducibility. Everything that we saw today is a part of lakeFS open source. So those samples that Amit shared, you can just run the lakeFS open source solution locally and run it with you. We also, of course, offer a hosted solution, which is a paid version if someone wants it, but the open source is an open core approach, meaning there are no artificial limitations within lakeFS. Or if someone wants to take advantage of some enterprise features like RBAC or SSO, you can also choose to run the enterprise version of lakeFS locally for your environment as well, which obviously comes also with lakeFS support. So look, we'll send over some links with the samples and so on for those of you who registered. Thank you very much for joining the call. It's also worth mentioning we have a pretty incredible Slack community. Would love to have you join. You can go there by going to lakeFS.io/Slack. Amit is there, I'm there. We have a help channel there that we're actually monitoring that in case someone doesn't answer in a timely fashion, we can also answer those questions also, although chances are that's not going to happen. I do want to ask one last question, which is, was this helpful for you guys? Because that helps us kind of focus on what types of webinars we do, approximately a webinar a month. This will help us focus on what type of content is the content that you guys want to hear and learn more about. So please take a few seconds to answer those questions. We'll hold tight and see if there's any last questions on the Q&A or on LinkedIn. Let's see. We'll appreciate answers. Was this helpful for you guys, or was this a waste of your time, or was this interesting but irrelevant for you at the moment? Let us know. Very helpful. Thank you, Camila. Excellent. Okay. So I will hold tight. Let's wait a few more seconds to see if anybody has any questions. For which companies would you suggest lakeFS? I will suggest lakeFS for any company at any size that uses data on top of object storage for this question. So the one requirement of lakeFS, right, is that the data needs to sit on top of object store, either on-prem or on the cloud, right? This can be S3, Azure Blob, Google Storage. It can also be MinIO, Dell ECS, NetApp, Hitachi, but it needs to be an object storage that we can connect to. So our smaller user, a smaller company, right? We have a lot of individuals that do this for their own simples. Our smaller companies that I'm familiar with as customers is a company of 3 users that does AI for pets, for early indication of disease in pets. And our largest company that I'm aware of is probably, I don't know, we have the US largest defense contractor is a lakeFS user. We have testimonies from Netflix. We have banks, insurance companies, car manufacturers. So I really think that any company size, as long as you have data that you care about, can benefit from this.
There was another question on LinkedIn. Does lakeFS have a schema identification feature?
Yeah, that's a great question. So what we do have is we have a way to do schema validation, right? So actually, I think Amit and I don't know if we ever had a webinar on this, but there's definitely, it's well documented. We have, there's something in lakeFS that we did not talk about at all called hooks, which is like the alternative of Git action, something that you run before a merge, after a merge, before a branch, after a commit. And one of the things that you can do is before you actually go and you promote data, you can verify automatically through a check that it's in the schema that you wanted. And if it's not, you can fail that merge.
And also we do some difference between the schema too. For example, for delta table, we'll tell you all the changes that happen.
Okay. Let's see if there's any other questions. I also appreciate that there's a delay between the Zoom and LinkedIn. So I will wait 20 more seconds, 30 more seconds. Okay. Lots of good questions, lots of good interest, lots of good feedback. So thanks, everybody. I hope this was helpful.